Hey everyone, today we are going to dive deep into multiple linear regression, vectorization, and feature scaling. I know this could be a bit complicated if you are learning it for the first time, but I have tried my best to keep it clear and easy to follow. By the end of the video, we will actually build our own regression model using vectorization and feature scaling, so you will get a solid intuition for how they work. If you saw our last video, we used a house example to explain simple linear regression. Today, we'll stick with the same example and see how multiple regression can be used here. Let's say you want to predict the price of the house, but this time not just based on area. In the real world, you would consider a bunch of features like number of bedrooms, floor, age of the house, parking area, and so on. That's exactly where multiple linear regression can be used. On the screen, you see our data. We have got 4 features here: size of the house, number of bedrooms, number of floors, age of the house. Together, these 4 factors determine the price. For example, a 3000 square feet house with 5 bedrooms, 2 floors, and 10 years old might cost $500,000. Just so we have a good mix, we have also included smaller houses in our data like 2000, 1000, and 500 square feet. Remember the simple linear regression formula? Y equal to W times X plus B, where X was a single feature like area. But now we have 4 features, so we will call them X1, X2, X3, and X4. The price still remains Y. So in multiple linear regression, our equation becomes y equal w1x1 plus w2x2 plus w3x3 plus w4x4 plus b, where w1 to w4 are their weights. And yes, just like before, we will use gradient descent to find the best values of w1 to w4 and b that minimizes the cost. We will get into the gradient descent in a moment, but I hope you are following where this equation comes from. In simple linear regression, the price depended only on one feature. Now it depends on 4. And if we have even more features, say n features, the equation looks like this, where n is the total number of features. Before moving on, let's get comfortable with the idea of vectorization. A vector here is basically just an array. Don't get confused with the physics definition of magnitude and direction. In machine learning, it's just a list of numbers. So, what do we mean by vectors in multiple linear regression? We mean arrays of parameters and features. Let me explain. So, our current function looks like this. In vector form, it becomes like this, where w arrow, which is equal to a list of w1, w2, w3, and w4 is the weight vector, and x arrow, which is equal to x1, x2, x3, and x4 is a feature vector. Both w arrow and x arrow are vectors. Also notice we are taking the dot product of these two vectors. If you are not sure what the dot product is, it's just multiplying each weight by its corresponding feature and then summing them up, like you see on the screen. But why do we even need vectorization? On screen, I have shown a code that calculates y for n features without vectorization. You would use a loop, iterate over all features, and update y step by step. That's fine for a few features, but what if you have hundreds or thousands of features? Sure, you could still use a loop, but it gets slow and messy. However, with vectorization, everything happens in one step. Seriously, all calculations are done at once, which means less computation and way faster processing. And you would write a whole loop like this. We just use NumPy's dot function. Well, I don't know about you, but I am lazy and I prefer writing less code. I hope that makes sense and you can see why vectorization is a best practice here. Now let's talk about gradient descent in this vectorized world. If you had 10 features, without vectorization, you would update each weight like this. But with vectorization, it becomes just this, where W arrow is a weight vector and D arrow is a derivative vector. By the way, if you're not sure what gradient descent is, I recommend watching a quick video on it first. Or check out my simple linear regression video where I explain it step by step. Looking closer at gradient descent update, the derivative still involves y hat minus y times x like simple linear regression for each feature. That repeats for all features, so it becomes a vector operation too. And b is updated just like in simple linear regression, b equal to y hat minus y or error. Now let's move to another important concept, feature scaling. Why do we need it? Often our features have very different ranges. In our example, area ranges from 500 to 3000, but bedroom ranges only from 0 to 5. This can cause large values like area to dominate the model. So what do? We scale the feature so they all contribute equally. This also makes the model train faster and more stably. We mainly use two methods for scaling. First, mean normalization. For each feature, we transform it using the formula you see on the screen, where mu is the feature's average and max min are its highest and lowest values. For example, if x1 originally ranged from 500 to 3000 with an average of 1000, after scaling it might range from minus 0.2 to 0.8, and x2 ranged from 0 to 5 becomes minus 0.6 to 0.4 with average of 3 bedrooms. Now all features are on similar scale. And second method for normalization is z-score normalization. Here we use formula as you see on the screen, where mu is mean and sigma is standard deviation. I won't go too deep into the math here, but both methods help us bring all the features into a common range, which makes gradient descent converge faster and more reliably. Alright, so that's the plan for today. We will take our house dataset, apply multiple regression with vectorization, scale our features, and build a model step by step. And again, we won't use a fancy library like Scikit-Learn today, just pure Python and NumPy. Let's jump into the code and see it all in the action. So let's start coding our multiple linear regression model. So I'll quickly import the NumPy module and define our X-train and Y-train dataset. Also, let's quickly log this X-train and Y-train dataset so we can see it in the console. Now let's define the scale features function. I will explain the function to you in a while. First, let me write the code. So as you can see in the function, we have taken np.mean function to calculate the mean. We have taken x0 in case of x because we want column wise average, not the row wise. Remember that. Then we have calculated the standard deviation mean for y as well. And we have used the z-score normalization that we understood a while ago and returned the values of x scale, y scale along with our matrices. Now let's quickly define the compute cost function as well. Again, I will explain it to you once I code it. Yeah, so if you see in the cost function, x, y, w are vectors and b is our normal scalar value. So when we calculate the predictions using the dot function, this returns a list and b is added to those predictions. Now to calculate errors, the prediction is a list, y is also a list, so they are subtracted, and error is also a vector or list. Now we use the cost function formula to calculate the cost and return it respectively. Now we will also see how to write the compute gradient function and how we can compute the gradient. So I have written the compute gradient function, and if you see, it's the similar logic to calculate the error, and we have used the same formula but in vectorized form to calculate the derivatives. Make sure you transpose the x, and we have written the value of the gradient part. Now let's calculate the actual function to calculate the gradient descent. So this is the function to calculate the gradient descent. We are taking number of iterations and we are calculating the gradient part, then updating the weights and bias using alpha. Now for our understanding purpose, I have also added the log statement so we can see the cost as per the iterations, and finally return the updated values of w and b. So I have now called the scale feature function and passed the xtrain and ytrain values to get the respective values of x scale, y scale and other stats and logged it so we can understand it. Now let's quickly initialize the initial values of w, b, alpha and iterations. By default, I am keeping the values of w 0, b let's start with 100, alpha 0.15 and iterations say 1500. So you can take any values. So I have randomly taken some values. I have initialized w as 0, b as 100 as you can see, and we can like tweak it later on. Now let's call the gradient descent algorithm function so it can give us w final and b final and log it. So I have called the function, and now finally let's predict the price of the data we already have, that is x train and y train. So I have written a loop that will calculate the price of each house using the w final and b final and print it on the screen. Now let's try to predict the price of a new house. That's area would be 1400 square feet, number of bedroom would be 3, floors would be 2, and let's say age would be 5. Now let me quickly write the code. So as you can see, I've defined the new house and scaled the features, then predict the prices. Remember, it's the scaled version, so we need actual values like 5000 and not 500 or 5. So I've got the actual value by multiplying to standard deviation, adding the mean, and predicted the price up to like 2 decimal points. Oh, by the way, one change, this is capital Y, not a small y. Remember that. Let's run our algorithm. Now our algorithm has worked successfully. We can see our x-train and y-train data, x scale values, iteration and their cost. Let's go to the final values. So the final values of w's turned out to be this, and b final became 0. We started with 100. And our predictions, if you can see, our predictions are pretty accurate, right? And the price for the new 1400 square feet house turned out to be $285,127.80. So let's try one thing. I think if I increase the iteration to let's say 2000, we could get more accurate values. Let's run it. So let's go below. And if you see, those are exact values our model have predicted. Along with the value of 1400 square feet, it reduced by like 2 cents, I think. And that's it. We have built our own model, predict the price as you would do in real world. Thank you for watching.